Hello, and today we will talk about statistics. Let's break it down. The normal distribution has a few defining characteristics. It's mathematically defined. Now, behavioral data rarely match the theoretical formula exactly, but they come close enough that we consider them normal for practical purposes. It's symmetrical. That means the data above the mean mirror the data below the mean. Another key point, the mean, median, and mode, all align at the center. Picture a curve perfectly split into equal halves. The total area under the curve equals 1.0. Why does this matter? Because the total area represents probability. We use it to predict outcomes. And then there are the tails, those thin parts that stretch towards infinity on both ends. Fun fact, the tails of a normal distribution never actually touch the x-axis, which makes it possible to observe those occasional outliers in your data. The standard normal distribution. Now that we understand the normal distribution, let's get specific with the standard normal distribution, also called the z-distribution. Here the mean is always 0, and the standard deviation is 1. This consistency helps us measure probabilities and compare scores across different datasets. You might hear the term z-score. Think of it as a way to locate a specific score on the standard normal distribution. It tells us how many standard deviation a score is from the mean. For example, a z-score of +1 means a score is one standard deviation above the mean, while a z-score of -1 is one standard deviation below the mean. These scores are useful because they allow us to calculate probabilities. For instance, what are the chances that someone scores above or below a certain value in a test? Or how likely is an outcome compared to the rest? The unit normal table. Here's where the unit normal table, or z-table, comes in. It's like your statistical GPS. This table lists z-scores in one column, the proportions of area between a z-score and the mean in another, and finally the area towards the tail. Let's simplify. Picture a z-score of 0, which sits at the mean. The total area above it equals 0.5, half of the curve. As your z-score moves further from the mean, say to z1, the area between the score and the mean grows larger. Want to find the proportion of data below the mean? Look at the same z-score but in its positive version, because the normal distribution is symmetrical. It's all about using the table to unlock probabilities. How to locate proportions. Here's a step-by-step guide to finding proportions with a z-table. Transform the raw score x into a z-score. Use the z-score formula. Find the z-score in the unit normal table. This tells you its corresponding proportion of area. For example, to locate proportions above the mean, check column C for the tail area. To locate proportions below the mean, use the same column but for the equivalent positive z-score. And if you're finding the proportion between two z-scores, let's say z equals +1 and z equals -1, just sum up the values from the mean to those scores. Easy, right? Real-world application. Why does this matter? In behavior science, it's all about interpreting data and predicting outcomes. Knowing how to use these scores and the normal distribution means you can analyze surveys, test results, or even experimental data effectively. And let's not forget the practical side, like comparing different data sets if you are studying exam scores or response times. Z-score help you make sense of it all, regardless of the units of or scale of measurement. Hi everyone, and welcome to Erasmus Insight. This is a part 2 and the chapter 7, Probability and Sampling Distributions. Sampling, from population to samples. Let's start with the basics. Sampling from populations. When researchers measure a sample, they're looking to make inferences about an entire population. But instead of measuring everyone in the population, which is often impossible, they work with sampling distributions. Here's the definition to remember. A sampling distribution is the distribution of all possible sample means, or sample variance, which you could calculate from samples of a specific size taken from the same population. A sampling distribution is the distribution of all possible sample means that you could calculate from samples of a specific size taken from sample population. Think of it as a meta distribution. It gives us a way to connect small samples to the larger population. A large population with a small sample group shows a dot or blocking being pulled from it. To avoid bias, researchers use random sampling methods. The most common is sampling without replacement, which means that once an individual is selected, they are not put back in the pool. The probabilities change as you go, making each selection conditional. On the other hand, we have sampling with replacement, where individuals are put back in the pool after selection. While useful for theory building, it's less common in behavioral research because populations are typically large enough to make this unnecessary. Designing your sample. So how do researchers actually select a sample? This is where the sample design comes into play. Essentially, researchers decide, does the order of selection matter? Do we replace participants after selection? In theoretical sampling, order matters and selected individuals are replaced. This approach is used mainly to develop statistical theories. But in behavior science, we're typically more practical, using experimental sampling where orders doesn't matter and participants aren't replaced. This method better reflects real-world population. The central limit theorem and the sampling distribution of a mean. Now let's talk about one of the most important concepts in statistics, the central limit theorem, CLT. The CLT says that no matter what the population distribution looks like, the distribution of sample means will approximate a normal distribution as the number of sample increases. This is why sampling distributions are so useful in inferential statistics, but let us calculate probabilities for sample means. Key points about the sampling distribution of a mean. The sample mean is an unbiased estimator of a population mean, meaning its value equals the population mean on average. The standard error of a mean measures how much sample mean deviate from the population mean. The smaller the standard error, the closer the sample means are to the population mean. Here this formula for the standard error. Two things that reduce the standard error: a smaller population standard deviation, a larger sample size, thanks to the law of large numbers. Sampling distribution of a variance. So what about variance? The sampling distribution of a variance tells us how sample variances compare to the population variance. Key point here, the sample variance is unbiased when we divide by degrees of freedom instead of the sample size. It's DF. Degrees of freedom account for the variability we lose by estimating from a sample. But keep this in mind. The sampling distribution of variances is positively skewed. Unlike means, variances don't form a perfect bell curve. It doesn't have minimum variance like the sampling distribution of a mean does. This means that while the average sample variance equals the population variance, individual sample variances can vary quite a bit. Let's put it all together with a powerful tool, the Z-transformation. The Z-transformation for sampling distributions allows us to find the likelihood of observing a particular sample mean without a population. Here's the formula. M is the sample mean, mu is the population mean, and OM is the standard error of a mean. Once we calculate the z-scores, we can use the unit normal table to find probabilities and proportions. This is a game changer for answering questions like how likely is the simple mean given the population parameters? What is the probability of observing a more extreme mean? Alright, here are the main things to remember from chapter 7. Sampling distributions connect samples to populations, letting us estimate probabilities. Use sampling without replacement for most behavioral research to avoid bias. The central limit theorem ensures that sample means are normally distributed with large enough samples. Variance in sampling distribution can skew, but it's better to calculate unbiased estimators using degrees of freedom. Finally, z-scores help us translate sampling distributions into meaningful probabilities. Whenever you're designing a study or analyzing data, these tools will be indispensable. Let's begin with the basics. Hypothesis testing uses samples to learn about populations. Why samples? Populations are too large or inaccessible, but thanks to the central limit theorem, we can use the sample mean as an unbiased estimator of a population mean. We have two key hypotheses. The null hypothesis, or H0, assumes no difference or effect, while the alternative hypothesis, H1, contradicts that. Here's the twist. We always start by assuming H0 is true and then check how likely or unlikely our data makes it. To decide, we use a level of significance. In social science, that's usually 5%, or alpha, 0.05. This means there's only a 5% chance of rejecting H0 when it's actually true, also called a type 1 error. Speaking of errors, there are three types. Type 1 error, rejecting H0 when it's true. Type 2 error, not rejecting H0 when H1 is true. And type 3 error, placing the rejection region in the wrong tail. By the way, the power of a test measures how likely we are to correctly reject H0 if it's false. Let's summarize the process. State H0 and H1, set the significance level, commonly alpha 0.05, and compute the test statistic. This depends on whether we're using a z-test or a t-test. Make a decision. Compare your obtained value on the critical value. Now let's move to Chapter 9 and discuss t-tests for testing means. We use these when standard deviation is unknown, a common scenario in behavioral research. Assumption for one sample t-test. Data follows a normal distribution, sampling is random, or observations are independent. In one sample t-test, degrees of freedom is n-1. Use plus minus 196 for two-tailed, alpha 5%, and 1 plus minus 65 for one-tailed tests. Switch to two independent sample t-tests. This test compares means from two groups. Remember, the groups are independent, meaning no overlap between samples. We test for the mean difference between population using four assumptions: normality, random sampling, independence, and equal variance. If you're using SPSS, look at the p-value from the Levene's test. If p is more than alpha, assume equal variances. Otherwise, use the second row. For the t-test itself, if p is lower than 0.05, reject H0. Otherwise, retain H0. What is estimation? Estimation is at the heart of statistics. Essentially, it's how we use sample data to estimate unknown values in a larger population. Think of it as using what we know to make an educated guess about what we don't know. Precisely, here are two main types of estimation: point estimation and interval estimation. Let's break them down. Point estimation is the process of using a single statistic from your sample, like the sample mean, to estimate a population parameter. For example, if you surveyed 100 students and their average study time was 5 hours, you'd use that 5-hour mean as a point estimate of the study time for all students. Exactly, but here's the catch. Point estimation is very precise, and that's both its strength and weakness. While it gives us an exact value, we can't be entirely sure it's correct because we're basing it on a sample, not the entire population. This is where interval estimation comes in. Instead of estimating a single value, we use a range of values called a confidence interval, within which the population parameter is likely to fall. A confidence interval provides both an upper and a lower boundary. For example, if we calculate a 95% confidence interval for our average study time as 4 to 6 hours, we're saying there is a 95% chance the true average study time falls within that range. Remember, the higher the confidence level, say 99% versus 95%, the wider the interval. This happens because we're increasing our certainty. So how do we calculate these estimates? First, for a confidence interval, we need the sample mean, our point estimate, the standard error, which accounts for how much the sample mean varies from a population mean, and finally, critical values based on the level of confidence we choose. Once we have those values, we use the formula. Population mean equals sample mean, etc., etc. This formula is the backbone of interval estimation. And here's a pro tip for students to memorize the critical values for common confidence level like 95 or 99. It'll save you time. Now let's switch gears and talk about ANOVA, or analysis of variance. A tool for comparing the means of multiple groups. Imagine you're testing whenever students from 3 different universities have varying average student times. That's where ANOVA shines. Instead of running multiple t-tests between pairs of groups, ANOVA compares the variance between all groups at once. Let's go over some key terms here. ANOVA calculates 2 types of variance. Between group variance, this measures the difference between the group means. Within group variance, this looks at the difference within each group. Using these, we calculate an F statistic, which tells us whether the group means are significantly different. If the F value is large enough, we reject our null hypothesis, which assumes all group means are equal. After rejecting the null hypothesis, we need a post hoc test to figure out which specific group differ. The Sheffield test, for example, runs pairwise comparisons between all group means. That way, we get detailed insights, like whether group A is different from group B, but not from group C. Remember, these tests are crucial because ANOVA alone doesn't pinpoint the differences, it just tells us there's a difference. Let's wrap it up with some quick study tips for estimation. Focus on understanding when to use point versus interval estimates, and for ANOVA, make sure you can explain the concepts of variance and F statistics. These are common exam questions. Great advice, and don't forget, practice is key. Work through some samples problems, especially those involving confidence intervals and critical values. And now the last part. Welcome to Statistically Speaking, where the world of data meets discovery. Today we're exploring 2 fascination topics: analysis of variance, or ANOVA, and correlation. If these terms sound intimidating, don't worry, I've got your back. We'll uncover what they mean, how they work, and most importantly, why they matter. By the end of this episode, you'll see these statistical tools as much more than just formulas. They're a gateway to answering real-world questions like, how do different teaching methods affect learning outcomes? What's the relationship between exercise and mental health? And why do some data relationships feel like our body is dead? To kick things off, let's start with ANOVA, short for analysis of variance. At its core, ANOVA answers one critical question. Are the differences between group averages real, or are they just the results of random chance? Here's the scenario. Imagine you're conducting research for a university. You're investigating 3 popular study techniques, using flashcards, attending group study session, and simply reading alone to see which leads to the better test performance. Now, if you're comparing just 2 groups, say flashcards versus reading alone, you'd likely use a good old t-test to determine if there is a significant difference. But what happens when there are more than 2 groups, like in this case? That's when ANOVA steps in. Think of ANOVA as a referee helping you determine whenever there is a statistically significant difference between group means. Here's how it works, step by step. Set up your hypothesis. ANOVA starts with 2 competing ideas: the null hypothesis, all group means are the same, and alternative hypothesis, at least one group mean differs from the others. Partition of the variance. Next, ANOVA separates the total variance in your data into 2 types. Between groups variance, the differences between the means of your groups. Within groups variance, the individual differences within each group. Calculate the F ratio. The magic lies in the formula, where MSB, mean square between groups, tells us how different the groups are, and mean square within groups accounts for the spread of data within each group. A higher F ratio indicates bigger differences between groups relative to differences within them. Decision time. Using the F value and your degrees of freedom, you calculate a p-value. If this p-value is smaller than your threshold, usually 0.05, You reject the null hypothesis, including that at least one group stands out. Here's the twist. ANOVA tells you if a difference exists, but not where it is. For that you need post hoc tests like Tukey's or Sheffice's test to pinpoint specific group differences. Let's bring this to life. Imagine a chef wants to test 3 marinades, teriyaki BBQ and garlic butter, on steak flavor preferences. The chef gathers a group of 30 participants and divides them randomly into 3 equal groups. Each group tastes steak with 1 marinade, then scores its flavor from 1 to 10. After collecting the scores, the chef runs an ANOVA test. What does she find? ANOVA reveals a significant difference between the groups. A post hoc test confirms that garlic butter reigns supreme, followed by barbecue, while teriyaki trails behind. By using ANOVA, the chef avoids guessing or making biased assumptions, instead of uses data to guide her decision. Now, let's pivot to correlation. If ANOVA is about differences, correlation is all about relationships. Specifically, correlation examines how 2 variables move together. For instance, does an increase in exercise hours per week lead to higher happiness scores? Or does more screen time lead to lower grades? The strength and direction of this relationship are measured by the Pearson's correlation coefficient, R. +1, a perfect positive relationship, -1, a perfect negative relationship, and 0, no relationship at all. Let's add some visual context with a scatter plot. Imagine each dot on the plot represents a data pair. For example, positive correlation, data points from an upward sloping line like hours studied and test scores. Negative correlation, data points slope downwards, think sugar intake and sleep quality. And no correlation, points are scattered without any discernible pattern, like shoe size and IQ. But here's the cautionary tale. Correlation does not imply causation. Just because 2 variables are related doesn't mean one causes the other. For example, ice cream sales and shark attacks both increase in the summer. That doesn't mean eating ice cream causes sharks to attack. So how are ANOVA and correlation connected? Both tools help us understand patterns in data. ANOVA breaks down differences across, while correlation quantifies the strength of relationships between 2 continuous variables. Imagine you're running a healthy study. You use ANOVA to compare calorie intake among 3 diets, and then use correlation to analyze how caloric intake relates to participants' energy level. By combining these tools, you uncover the full picture. Every great method comes with challenges. For ANOVA, ensure normality and equal variances across groups. Use a log or square root transformation if these assumptions are violated. For correlation, beware of outliers. A single extreme data point can skew results dramatically. Always examine your data visually and double-check your assumptions. Statistical tools like ANOVA and correlation unlock the hidden stories in data. Whenever you're comparing means or exploring relationships, these methods are essential in psychology, business, and healthcare. That's it for today. Thank you for listening.